My name is Natsumi Onosato from Keio University. It is a great honor to be here to present my research. Today, I'd like to talk about the detachable robot that moves a baby bouncer. Let me begin by talking about background. A baby bouncer is a type of cradle designed for infants. It allows soothing through gentle rocking, either caused by the baby's movement or by a caregiver's hand. Under parental supervision, an automated baby bouncer helps soothe the baby for short periods, such as during household chores or bath time, when direct attention to the baby is difficult. Currently, electric baby bouncers are available on the market. However, they tend to be expensive, large, and heavy, making them less practical for home use. To address these issues, we propose an external device that can be attached to existing bouncers, enabling automated locking functionally. Next, let me discuss related research. We investigated related works from two perspectives. The first is external devices using submotors for functional enhancement. Examples include a robot that attaches to a chair to create vibrations, as shown on the left, and a system that uses a submotor to instantly transform soft bristles into stiff ones, as shown on the right. The second perspective is related research on baby bouncers. There has been research on using existing electric baby bouncers combined with image-based facial recognition to adjust the locking motion according to the baby's condition. Additionally, studies on the safety of infant products have included baby bouncers. For example, one study analyzed data from real-life fatal accidents and found that the primary causes were the lack of safety harness use and insufficient parental supervision. Based on these findings, we consider the risk associated with baby bouncers and emphasize the importance of using our proposed device under parental supervision. By doing so, we aim to focus on the advantage of soothing infant safety and effectively. This research investigates the use of an external device to automate the locking of the baby bouncers and examines the impact of the device on the baby bouncer. The proposed device offers several advantages. It is detachable, easily automated existing baby bouncers without requiring modifications, and is more affordable compared to electric baby bouncers. Now, let me explain the proposed method. We attach a device equipped with a submotor to the baby bouncer. Oscillations generated by the submotor's rotation are transmitted to the baby bouncer, enabling it to lock automatically. Regarding implementation, the structure of the device is as follows. We mounted a submotor on an arm and indirectly attached a weight to the rotation part of the motor. An accelerometer was installed at the apex of the clamp for measurement. The constructed device is placed at the top center of the baby bouncer for optional performance. Next, the system overview. The accelerometer and submotor are controlled via Arduino. The submotor adjusts the rotation angle and rotation cycle, while sensor data from Arduino is transmitted to a PC for analysis. Finally, here is a demonstration video of the devices in use. As you can see, the device successfully moves the baby bouncer. Next, I will explain the experimental overview. To flexibly replicate the weight of a baby, We used one 3 kg bathing doll and 5 2-liter bottles filled with water. This setup allowed us to simulate various weights. The baby bouncer used in this study has 3 adjustable incline settings, referred to as high, middle, and low, from the set post angle downward. To examine the rocking motion of the baby bouncer and the impact of the device on the baby bouncer, we conducted 4 experiments. Let me explain each one in detail. First, we investigated the effect of the device on the rocking frequency of the baby bouncer. In this experiment, the rotation cycle of the device was fixed. While the baby bouncers incline, the baby's simulated weight and the submotor's rotation angle were varied. We also measured the device's rotation cycle for comparison. For this, an accelerometer was attached to the rotation part of the device and secured to a fixed surface using a clamp for accurate measurements. The method used was to perform a fast Fourier transform using the acceleration data, and a first peak obtained was considered to be a bouncer period. Now the result and discussion for experiment 1. In all scenarios, the rocking frequency of the baby bouncer matched the rotation cycle of the device. This finding demonstrates that the device can synchronize the rocking frequency of the baby bouncer with its own rotation cycle. Next, we investigated the changes in the rocking frequency of the baby bouncer caused by varying the baby's weight. We analyzed the baby bouncer's natural rocking frequency when the simulated baby weight was changed. The method involved rotating the device for only half a period and then analyzing the period of the baby bouncer using the fast Fourier transform. The period of the baby bouncer was calculated using this process. Results and discussion for experiment 2. We found that the rocking frequency of the baby bouncer was significantly attached by changes in the simulated baby weight. Specifically, lighter weights result in shorter cycle, while heavier weights led to longer cycle. Next, we investigated changes in the amplitude of the baby bouncer's rocking when the device's cycle was varied. This is because we thought that matching the period of the baby bouncer to the period of the device would result in a larger rocking. We adjusted the baby bouncer's incline and the sub-device's rotation angle while varying the simulated baby weight and the device's rotation cycle to calculate the amplitude. We used the steps described on this slide to estimate the amplitude using video images. Result: we found that as the simulated baby weight increased, the cycle and produced the largest amplitude also increased. Additionally, the amplitude at this optional cycle was significantly greater compared to other cycles. To further investigate the hypothesis that aligning the baby bouncer's rocking frequency with the device's rotation cycle would result in larger rocking amplitudes, we compared the baby bouncer's natural frequency from experiment 2 with the cycle that produced the maximum amplitude. As a result, the error was within a range that can be said to be almost negligible. From this, it can be said that it is possible to produce larger rocking by matching the period of the device and the period of the baby bouncer. Finally, we investigated how changes in the rotation angle of the device affect the amplitude of the baby bouncer's rocking. From experiment 2, we determined that the rocking frequency of the baby bouncer changes depending on the simulated baby weight. From experiment 3, we confirmed that aligning the device's rotation cycle with the baby bouncer's natural frequency produces larger rocking amplitudes. However, large rocking motions are not always desirable when using a baby bouncer. Also, it would be useful if your rocking motion could be adjusted based on the intended purpose, such as soothing or putting a baby to sleep. Therefore, we investigated how changes in the rotation angle of the devices affect the amplitude of the baby bouncer. Result: we found that increasing the rotation angle generally resulted in larger rocking motions, while decreasing the angle resulted in smaller motions. That indicated that adjusting the device's rotation angle allows for control over the amplitude of the baby bouncer's rocking motion. Discussion on constraints. There were 3 main constraints identified. 1. Electronic noise from the submotor. The submotor produces significant noise which is not ideal for soothing babies. Moving forward, we will explore the use of load output submotors or alternative oscillation source to address this issue. 2. Device size. In the future, we will aim to develop a compact device that can be integrated and sorted seamlessly with the bouncer. 3. Amplitude control. Large rocking motions are not necessarily the best for soothing babies. Therefore, based on the experiment, we would like to eventually develop a mechanism that can automatically control that amount of bouncing of the bouncer according to the weight of the baby. I'd like to close my presentation. Thank you for your attention.